Okay, good morning. So last class we discussed about scattering parameters. So scattering parameters, it is a method of characterizing your circuit performance. So where does it characterize? At high frequencies. So in your waveguide, at high frequencies, the method of characterizing your circuit performance is your scattering matrix, and your scattering matrix are related with the power. So this is all what we discussed in the last class. And your scattering matrix, it is a mathematical construct, right? So now we'll see the properties of your scattering matrix. So the first property is, so it should be a square matrix. Your S matrix should be a square matrix of order n cross n. Suppose we say it is a 2-port network, we will have 2 cross 2. If it is a 3-port network, we will have 3 cross 3. Likewise. So S is always a square matrix of order n cross n. And the next property, your S matrix should be a symmetric matrix. So when we say 3-port network or 2-port network or whatever it is, so your Sij will be equal to Sji. And if it is satisfying this property, then it is called as a symmetric matrix. And the next property, your scattering matrix is a unitary matrix. So if you multiply your scattering matrix with its complex conjugate, you will get a unit matrix. And the next property, if suppose your third port in your H plane or E plane, your third port, say this is your H plane or E plane. So your third port, which is attached to the main collinear arm, so this port will be perfectly matched to the junction. So in that case, your Sii will be equal to 0. It means this is the third port. Third port is attached to the junction, right? So we'll have S33 will be equal to 0. And the next property, the sum of the product of each term of any row or column multiplied by the complex conjugate of the corresponding term of any row or column is going to be 0. Okay, so if you are having a different row, different column, if you are multiplying the rows and columns, and we are summing it for different rows and different column, it will be 0. That is, when your k is not equal to j, it will be equal to 0, and it will be equal to 1 if your k is equal to j. Okay, so for same row, same column, it will be equal to 1. If it is of different row, different column, if you are multiplying the components with a different row, different column, that will be equal to 0. So these are the main properties of a scattering matrix, and we are going to see how this property is reflecting in your components. So the first component we are going to discuss is E plane T. So we'll see how your scattering parameters is going to impact your E plane. So you know this is your E plane. So E plane, it is by attaching a simple waveguide to the broader dimension. See here, you are going to attach and waveguide to the broader dimension of the main arm or a collinear port. So this 1 and 2, it is called as the collinear ports. So if you attach a waveguide to the broader dimension means this side, so then it is called as your E arm. Okay, E arm or side arm, we can call it of any type. So E arm or side arm. So this is even sometimes called as a difference arm. Suppose if we attach your waveguide at your narrower dimension, then that is your H plane. Okay, so E plane, it is by attaching a simple waveguide to the broader dimension of your rectangular waveguide, which is already having a 2-port network. Okay, so those 2-port network is your collinear port. So the port 1 and port 2 is your collinear port, and the third port which is being attached, that is your E arm. It is also called as a side arm or a difference arm. Okay, so what is the property of your E plane? Suppose if I give input at port 3, right, if I give input at this place, so my waveform will be equally divided among port 1 and port 2, but opposite in phase, right? That is why we say your port 1 and port 2 are 180 degree out of phase with each other. And here, as the axis of side arm is parallel to the electric field, this junction, it is called as E plane junction. Okay, so the main important property here is when we give input at port 3, it will be equally divided in magnitude but opposite in phase. Same way, what will happen if I give input at port 1 and port 2, same amount of input at port 1 and port 2. Say for example, if I give amount 5 volt at port 1, 5 volt at port 2, right? So what it will have to do, it is 180 degree out of phase with respect to your 3, right? So 5 volt minus 5 volt will be given at, it will be coming at a port 3. So we will have 5 minus 5, it is 0 volt. So that is why we call this side arm as a difference arm. Okay, so your side arm is called as a E arm or a difference arm, and your E plane T is also called as a series T. Right. So now we'll see the scattering matrix of your E plane. So what is my first property? The scattering matrix should always be a square matrix of order n cross n, right? So here it is a 3-port network, so we'll have order 3, so 3 cross 3 matrix. And what are all the possible parameters? Since it is a 3-port network, you should have n possible parameters. So these are the parameters of my scattering matrix. So yes, ranging from S11, S12, S13 to 3, S31, 32, 33, right? So next we know that your port 1 and port 2 are out of phase by 180 degree with your input at port 3, right? So because of this property, so your port 1 and port 2 are out of phase by 180 degree with input at port 3, right? So because of this property, I can say S13 is equal to S23 in magnitude but opposite in phase. So I can write like S23 is equal to S minus S13. And also we discussed in your E plane T, the third port which is attached to the junction, it is perfectly matched. So when it is perfectly matched, we know the property SII should be equal to 0. So I can say S33 equal to 0 because my third port is attached. And coming to the next property, your scattering matrix is a symmetry property. It is satisfying the symmetry property. It means Sij is equal to Sji. So in this 3-port network, I can say S13 is equal to S31, S12 is equal to S21, S23 equal to S32, right? So considering all these things, we can rewrite your scattering matrix. So considering all this, I have replaced it and I have rewritten my scattering matrix success. Okay. So now my next property, if I multiply your scattering matrix with its complex conjugate, I will get unit matrix. So this is my matrix now after replacing all the components which we have found out and multiplying with its complex conjugate, I will get a unit matrix. Okay. And what is the next property? If I multiply that rows and columns, if I multiply same row same column, I should equate it, the summation to 1. If I am multiplying different row different column, I should equate it to 0. So that is what we are going to use now. So I will do R1 C1, so same row same column. If I multiply this, I should equate it to 1. So if I do R1 C1, it is S11 S11 star, S12 S12 star, S13 S13 star equal to 1, right? Same way I can do it for R2 C2, R3 C3 for same row same columns, and that I should equate it to 1 because it is same row same column. And the sum product of the summation for different row different column, I should equate it to 0. So here it is 0, not 1, it is 0. Okay, so I am doing it for row 3 and column 1. So I am getting S13 S11 star minus S13 S12 star, which is equal to 0. I have to equate it to 0 because it is different row and different column. Now I am comparing this equation number 6 and equation number 7. From comparing this, what will happen? This 1 2 1 2 will get cancelled, this 1 3 1 3 will get cancelled. So I will get S11 square plus S22 square equal to 1. From that I can write it like S11 equal to S22. Yes, yeah. And from this equation I can solve S13. So it is 2 S13 square equal to 1. From there I can calculate your S13. So S13 is equal to 1 by square root of 2. Yes. So I have calculated this one parameter, right? So I can just replace this parameter here. Yeah, right. So I have to replace that. So in that equation I am taking S13 as common, and we also know that S13 is not equal to 0 because your value of S13 is 1 by square root of 2. So this one will not be equal to 0, so definitely this should be equal to 0. So while equating it, I am getting S11 is equal to S22, and in the previous thing we saw even S22 is equal to S11, right? So S11 is equal to S22 equal to S22, right? And I have S13 is equal to 1 by square root of 2. Now if I substitute all these components in equation number 6, then I am going to get S11 square plus this one is actually S12, right? So I can replace S12 as S11. So S11 square plus S11 square plus this is 1 by 2, right? It is S13 whole square, right? So it is S1 or 1 by 2, which is equal to 0. So if I substitute and if I equate it, I will get S11 is equal to 1 by 2. So now I know what is S13, I know what is S11, right? So here S12 is also equal to S11 and S22 is also equal to S11. So all the 4 unknown parameters I have found now. So S13, S11, S12, S22, everything I have found out. I can replace that in the square matrix, scattering matrix. So after replacing, I am getting a matrix like this. So this is my matrix of E plane T. Okay. So now with this scattering matrix, I can write the equation for my reflected wave. So my reflected wave, that is B, is equal to the square matrix into my incident wave. So this equation I know. So how many ports I have? I have 3 ports. So I can write your reflected wave as B1, B2, B3 and scattering matrix, and your incident wave as A1, A2, A3, right? So from this I can write as a equation for all this B1, B2, B3, everything. Yeah. So I can write my B1 is equal to, so I multiply and write it. So it is A1 by 2 plus A2 by 2 plus A3 by root 2, and your BT will be A1 by 2 plus A2 by 2 minus A3 by root 2. Yeah. And my B3, because I have only first 2 components, and A3, this one is 0, S33 is perfectly matched, so that is 0. So I can write A3 by square root 2 minus A3 by root 2. So this is the equation, my reflected wave equation. So with this equation, I have to see whether the scattering matrix is following the property of my E plane. So I'll just assume few cases and solve, see that whether it is satisfying the E plane properties. Okay. So now with this equation, I will take some cases and I will solve. So I am considering case 1. So for case 1, I am telling my A1 it is equal to 0, and my A2 it is equal to 0, and A3 it is not equal to 0. What is the meaning of this? So I am not giving input at port 1, port 2, but I am giving some input at port 3. So if this is the case, what is happening to my reflected wave? That is my B1, B2, B3. I have to substitute all this thing in this B1, B2, B3. Okay. So if I substitute, what I will get? B1 is equal to, because A1 and A2 is 0, so this and this will become A0, and I will have only this value, right? So B1 is A3 by root 2, and my B2 is minus A3 by root 2, and B3 it is 0. So from this, what did you understand? If I give input at port 3, I am getting output at port 1 and port 2, which is having equal in magnitude but opposite in phase. It is A3 by root 2, it is here minus A3 by root 2, right? So does it satisfy the property of E plane? Yes. So I am getting equal in magnitude wave at B1 and B2 but opposite in phase. So this is case 1. So let me take one more case. So case 2, I am assuming A1 equal to A2 equal to A, and A3 it is not equal to, A3 is equal to 0. So what is the meaning of this? I am giving some input at port 1 and port 2 but not at port 3. So what will happen in your E plane, if I give input at port 1, same amount of input, right? Same amount of input at port 1 and port 1. Port 2, what will happen at port 3? So it will take the difference, right? A minus A, and that will be equal to 0 here. That is why your E plane is called as a difference arm, right? We will see whether it is satisfying that property. So substitute these three in the equation and find out what is B1, B2 and B3. So your B1 is A by 2 plus A by 2. My B2 is A by 2 plus A by 2, and my B3 it is A by root 2 minus A by root 2, which is equal to 0. Does it satisfy? If I am giving input at port 1 and port 2, the equal amount of input, so at port 3 it is doing the difference. So that is why this is called as a difference arm. Okay, so when there is equal input at port 1 and port 2, which is resulting at no output at port 3. So this is one case. This is also satisfying the E plane matrix. So let me take another case. So I say A1 is not equal to 0, A2 equal to 0, A3 equal to 0. Let us consider this. What is the meaning of this? I am giving input only at port 1. I am not giving at port 2 and port 3. So what will happen? So maximum amount of output I will get at port 2, some amount will be going through port 3, and because there is no matched termination, again I will get some reflected wave, right? So let us see whether I am getting that. So if I substitute, what will happen? What is B1? B1 is A1 by 2, B2 is A1 by 2, and your B3 is minus A1 by 2. So what did you understand from this? So I am giving input at port 1. So I will have maximum output at port 2. So see here at port 2 it is A1 by 2. And at port 3 I will have some minimum amount. Some amount of wave will be reflected to the port 3. So it is minus A1 by 2. But I even have some output at port 1. What is that? It is a reflected wave. Okay. So likewise you can take for different cases and see whether it is satisfying your E plane property. So with this we'll stop your E plane property.